So, you folks will have reviewed some videos just recently and in preparation for this class. So what was that video on that I sent to you? State charts. State charts. So, what are state charts? And where do they, what function do they play? What role do they play within agents? Anyone? Okay, yeah. So it captures the state in which an agent, or in fact, the whole, other elements of the model can be in. The model as a whole, for example. Depicting particular them, often a fairly small number, maybe 20 or 5 or 3. And then we have these transitions between them. Can anyone comment for me? What are some transition types? One of the things I was hoping you could come away with from that lecture. What are some transition types? Okay, a message transition, which is triggered by some interaction, say from another agent or from the environment. Another one? Timeouts. Okay, timeout lets you transition after exactly some period of time after you got into that state, right? So we have a given state, and then we have a transition out of it, and this transition applies only if you're in that state. Conditional on you being in state, you may transition out. A timeout would mean you leave after exactly some period of time. How about others? An event. So there are certain events that will trigger it. One would be an arrival event. You arrive at a destination. Another would be you receive a message. So those would be examples. And those are two types. How about others? A condition. Yes, a condition. Under a certain condition, you'll leave. So if something is true, then at that point you'll leave. In a rate, with a certain chance per unit time. Where have we seen that before? That sort of chance per unit time in a system dynamics model and a first order delay. Yeah. And we'll be rehearsing some of these linkages. So that's good. There's many types of transitions, and each of them has its place. And today we'll be reflecting some on the impacts of those transitions on dynamics and their relationship to system dynamics models, particularly with first order delays. Okay. So that's good. So I was hoping now to start up the first of two examples. And depending how quickly we go, I hope to get through both examples today. If not, I'll refer you to a video for the second example, which is less long. So, ladies and gentlemen, I would like to begin, surprisingly, with a model which has system dynamics elements in it. So we're going to create a new model here in AnyLogic, and it's going to be called transitions and states and transitions and state chart comparison, or something like that. Comparison. And I'll say CMPT 858, 394, 858 for 858 T1 214. Okay, great. So we're creating this model. And I'd like it to include a very simple stock and flow model. Okay. So we're going to have two stocks connected by a flow. And that we're going to then compare this successively to a set of agents, the behavior of a set of agents. So the first stock is going to be called healthy, okay? And the second stock is going to be called, in a very sort of blunt way, ill, okay? And I'm going to connect them up with a flow here, which will be called um, uh, contracting illness or something like that. Okay? So I'm going to set it up something like that. You'll notice, by the way, we've seen it before, but I'll just rehearse it for people, that when we do this, once these things are connected properly, they're quite flexible. Before they're connected, there's a cloud there, and initially that cloud was there, but I was able to drag this guy atop the center point of that, the sort of point associated with that cloud, and it replaced it by a connection between these two. Okay? Now, I'd like to make it a first-order delay that's linking these two with a mean time to become ill of 20 years. So tell me the steps I need to go through to make that happen. I want people to go from the left to the right with a mean time they spend in a healthy state of 20 years. So what would I do? Okay, add a parameter. Great start. So I'm going to add a parameter here. And it will be called, I don't know, mean time healthy or something like that. It's a very stylized model. It's almost insulting to our guests from the health sciences. But all the mean time healthy. Okay, what do I do next? Okay, and from whence would that link go, and whither would it go? Whither would it go? Good. Okay. Excellent. And according to the principle of wanting these diagrams to kind of illustrate at a high level what's going on before we necessarily go down into all the details, where would there be another link required? Yeah, healthy to contracting. Give me an intuition for why there would need to be a link there. That's pretty nifty. Why would there need to be a link there? How if there were no link? What would that be implausibly stating? Yeah. That regardless of how many people are healthy, the number of contracting illness will be the same. And unless it's zero, that's very unlikely, because if the number of healthy people were zero itself, for example, anyone going here would bring this into the negative region, which is implausible. So typically with physical quantities, important point, with physical quantities that are exhaustible, where there can only be so many of them, so few of them, you need a delay, a first-order delay, and a negative feedback associated with them, so that if they're exhausted, there's no more flowing out. So if there's no more healthy people, there's nobody getting sick. Not all quantities are of that sort. Not all quantities are exhaustible in that sense. Can anyone give me a quantity that's not this sort of exhaustible quantity, this quantity that only has a certain amount of it? Can anyone give me an example? Those from physics work with it quite a bit, actually. Position, for example. You get a sort of a position in positive direction, position in negative direction. Amount of money that you have in your name, that can be positive or unfortunately negative. Right? It doesn't automatically stop if you go into negative territory, as those with credit cards will recognize. So there's quite a few quantities which can go negative because they're not physical quantities. But when we have physical quantities, just look for that negative feedback. Why is this a negative feedback from healthy to contracting illness? What's the link from healthy to contracting illness? What sort of link is that, plus or minus? From healthy to contracting illness? If there's more healthy people in the population at risk, the number each year who develop illness, remember contracting illness is a flow, it's the number of people per year, is that going to be higher or lower? Higher. Okay, so it's a positive link from healthy to contracting illness. By contrast, the link from contracting illness to healthy is what sort of link? It's negative. The larger the number of people per week that are contracting illness, the smaller healthy will be, right? So you should be able to recognize that's a negative feedback there. Okay, great. So tell me now the formula for this. So I like to rehearse these things because you're going to be asked to rehearse them on exams. And it's better that we nail it down so I don't have to wince when I see it. And not, so what's the formula? Good. Give me an argument why. Why isn't it times?
Because healthy over mean unhealthy would be the average for the amount of people that are going to leave for math rate.
Okay, that's true. But can anyone give me an intuition for why does it have to be divided by it? How about from dimensional considerations?
Mean time healthy at the time and
healthy
at number.
Yeah. And so the flow is people per unit time. So it's got to be divided by. You can't have multiply by. Please tell me that. Please. Yeah. Remember that? Yeah. It's an easy way to remember it. It's just got to be because if people, time, multiply, nah, you're not going to have people time. Cumulative hours worked or something. You can't have that as in other models, but it's not here. You're not going to have that for the relationship with the flow or first order delay. Okay? So this is people per unit time. It's got to be a divide. Does that make sense? Okay. Great. So tell me, ladies and gentlemen, what thing is missing still? Initial value. Good. So into that initial value, we shall put, for the left, 1,000. For the right, 0. Okay. Meantime healthy, 20 years. Okay, so what do I have to do to make, I say 20. What do we do to make it 20 years, to make sure it understands we mean years? Yeah, we go to the whole project, yeah. By the way, you can say, this is a pretty nifty thing, folks. It's a pretty nifty thing. Watch this. 20 times year. And no matter what the time units are as you model, it will know it's 20 years. If you want it to be 20 months, you can do 20 times month. It will make it 20 months, whatever time units the model uses. So you don't have to do it by changing the whole time units of the model to have it be semantically meaning 20 years, but I'm going to change this to be years so that if I just say 20, it actually is 20 years. But in any case, I can enforce it. No matter what the time unit of the whole model was, I could say 20 times year as a method, and it will be enforced. It's pretty nifty. Okay, people comfortable with this? Can we run this? What shall we see when we run this? Can anyone characterize the dynamics ahead of time? Good. And the number of people ill will be, okay, and will it be increasing faster and faster, or will it be increasing slower and slower? Good. Okay, let's create a little graph that will show this. So, where do we go to create a graph here? Yeah, so we go up to the analysis. Whoops, it's right at the top there. Right, not total top, but near there. Okay, great. So it's this guy here, and we're going to drag in a time plot, right? Boom. Okay, there we go. And great. Okay, so I want to do this plot stocks, right? Plot stocks, sure. And I'll add a data item, and I'll want to plot a value. So what do I want to plot first? Healthy, right? Control space is your friend. Add another data item. I want to plot ill. Okay? People comfortable with that? Okay, let's run this thing. Let's see if the prognostication proved correct. Okay, we didn't actually set the parameters of the time plot, so it would it would show it really nicely if we ran it for a long time. But this is what we see, and it matches what our esteemed representative from the School of Public Health indicated. Right? She's bang on as she is wont. Okay, so good. So we have this little model which captures that, and nothing should be new there, right? Any questions about where we're at so far? Okay, now we're going to venture into new territory. Ladies and gentlemen, we're going to now create an agent, and the agent will be associated with a state chart. And the state chart structure will mirror that seen in this stock and flow diagram. So they're going to have a healthy state, and they're going to have an ill state, and they're going to transition between them, each agent. And we're going to want to plot now, on that very same graph, the number of agents in the population with certain characteristics, namely those who are healthy, the count of healthy, and the count of ill. Because remember, wherever we have a population, we can compute these higher level statistics. So, ladies and gentlemen, I'd like you to tell me what to do. What do I do? Okay, so let's go create an agent. Good. New agent type, and we're going to call that without this aspersion to our veterinary colleagues, we're going to call it person. Okay? Okay. Great. So, I want these people to have a visual representation so we can see them visually. I want their visual representation to be based on, we could use any number of different things, but I'm going to, I think, for simplicity, use an oval again. Okay. Those of you who are interested in these things will find a huge number of different little diagrams or representations of people, of nurses, of doctors. Those are just a little bit more difficult to color conveniently. It's actually quite straightforward. You'll find plenty of videos where I show that, but I don't want to get distracted because we have limited time, and I do want to get through both exercises if possible. So I just added this. Great. Terrific, folks. That's a good start. And I would like this population to be a population of size. I want there to be a population of size 1,000 of these people. And just so we could see them easily, I want them to be randomly distributed around the screen. How do I do this? Good, good. Okay. Okay, so we're going to drag person into main, and we'll call it population, and it will be a population of agents of size, say, 1,000. Okay, great. Very nice to have a parameter called population size, change, but for expedience, we'll just say 1,000 here. Okay, great. And we have to say it's a population of agents, right? Rehearse, rehearse, rehearse. So rehearsing what we've done before to build your skills. Okay, so population of agents, great. And now we want to scatter them around the screen. Tell me one way to do that. Okay, we could do random layout in main, absolutely. But I'm going to show you, so Yuli is exactly right, and he's bang on, and that's what we did last time. And it shows he has been paying attention. Let us try it a different way. I'm going to show you a different way now, which is actually going to be more amenable to our needs, okay? And we'll see why in a few minutes. So ladies and gentlemen, with the population selected, I'd like to go down where it says initial location, and I'd like to say in the specified point, and I'd like to put these people uniformly distributed between 0 and 500 for their X location and their Y location. Their Z location we can leave as 0, as we will not be exploiting the full richness of the three-dimensional representation. Okay? 0 to 500 and X and Y. Where am I? I'm in population. I scroll down to this area called initial location. Okay? People okay with that? Great. Okay, ladies and gentlemen, can we run this model now? Yes or no? Can. Cannot. Can. Okay, there we go. We should see something like that. Do you see that? Okay, great. Okay, fantastic. Okay, so that's a good start. We have agents. The agents are shown visually. Let us now lend these agents some behavior, folks, in the form of a state chart. Let's give them a state. Let's allow them to be in a state, and let's allow that state to evolve over time. So what states do I want? I want two states in the same way that mirrors that socket flow diagram. So what are the states that I want? Okay, good. So let's go add some states. Go down to the state chart area and add in a state. Just call it health state, right? Healthy, and then drag in ill here. Okay. How many people would like me to go a bit slower? Okay. So thanks for the feedback. So I went to the palette, went down to the state chart area. I dragged in an entry point, and then I dragged in a first state. I dragged in a second state. Now I'm going to drag in a thing between them, and it's going to be called a transition, whose name is going to be contracting illness. Okay. You notice because it's within person, it doesn't clash with the external one. Okay. So, ladies and gentlemen, if I want this model to be comparable in its overall behavior to that stock and flow model, what type of transition should this be? A rate transition, good. And what should the rate be? What's the chance per unit time of them going from one state to the other? 5%. Sorry? 5%. Okay, good. It is 5% per year, yeah, so that's good. But suppose I want to do it in terms of the parameters that we already have in there. It'll be, where did that 5% come from? Healthy or... Okay, it'll be, this is a rate. This is a chance per unit per year. 1 over, and how do I get it? I get main dot, and then, what do I call it? Mean time healthy. Oh, gotta be a bit careful. Make it 1.0. In this case, it's fine because it's a double precision value itself. But you might want to, in general, you got to be a little bit careful like that. If you write 1 over 3, computer scientists, speak to me as if in unison. If you put 1 over 3 here, what would it? 0. It will give 0. Why? Integer division. Right? It would divide it as integer. So you got to be a little bit careful about that, and it doesn't hurt to be very specific. So you don't have to worry what this is. It's clear. It's a floating point division. Okay, ladies and gentlemen. So that's great. Shall we have people's color depend on their state, and we can actually see if they're evolving? How would we do that? Okay, yep, we could do it with a variable color. That's scalable with the number of states, so let's put in a variable color. And what type should that variable be? Other? Should be other. And it should be, and what's the type? With a capital C. Okay, and we're going to make its initial value black, say. And then how are we going to change that so that it changes? Sorry? How are we going to make it change when they change state? Each of these states has a handler, an action when you enter it. So you're going to say color equals, say for this one, green, semicolon, because it's an action, doing something. It's a statement. It's not really computing a value. And for ill, we're going to say color equals red. Great. Ladies and gentlemen, what's the final thing we have to do? So let me rehearse that again for people. Make sure you got that. I dragged up a value from this general area. I made the type of that value be capital C color, and I made its initial value be black. So it's an other type, namely capital C-O-L-O-R. When they enter the healthy state, we set the color to be green. When they enter the illness state, we set it to be red. But is that going to change their color right now?
No.
What do we still have to do? Yeah, we have to go to the oval and actually make that the color. So we go to the oval, and then for the fill color, we click next to it to become a dynamic value, and we say color. Okay, great. I'm trying to rehearse skills, but I'm trying to get to a conceptual point here where we'll be learning some important concepts. Okay, great. So, ladies and gentlemen, can we run this model? Run early, run often. When you have these models, you're going to want to run them over time. You're going to want to build frequently. This builds button up here, it'll tell you if there's a mistake. Okay, if there's a mistake, not in the semantics of the model, it'll tell you if there's a mistake in the phrasing of the model, the syntax of the model. Let me make this full screen so it's more palatable. Okay, great. So let's run this model now. What should we see? Okay, why do we see that? What's happening? What's happening? No, Christmas is not happening. What's happening? Okay, people are getting ill over time in a larger and larger number, and if we go and we zoom down to this, we'll find that a large fraction of the population is currently ill. Okay, so good. That's great. People start healthy, but they go to ill. Okay, now, ladies and gentlemen, we want to show the number of people who are ill over time and the number of people who are healthy over time according to the agent-based model. How would we do that? Anyone? Good. Excellent, excellent, excellent. I see some good ideas here. We're going to be plotting it up here. So it turns out if you go to the population, you can associate a statistic with the population. And we're going to create a statistic associated with this population called count healthy. And this is going to count the number that match some criteria. Okay? Now, how do we phrase this criteria? Well, within the criteria, we can use item, I-T-E-M, to indicate the current object that's the candidate for consideration. And it needs to tell it true or false. True if that object item is to be counted, false otherwise. Now, item here refers to the elements of the population, which in this case, what? Persons, people. So we could say item dot health state. Probably should have called it health state chart. Dot is state active, and give it the name of the state. The name of the state is going to be person.healthy. Healthy with respect to the person class. For those who are from computer science background, this is a static variable. Static, meaning there's one value across the entire class. So hence person.healthy, not item.healthy. It's not like each person has a thing called healthy. Specifically, it's the whole personhood has a notion of healthy, and that's what we're referring to here. We're saying, is this person's health state in the state healthy? Are they in the health state chart? Is it healthy? That's what that health state is. I should have called it health state chart. Is state active? In other words, is that state chart in the state that have an active state called healthy? People comfortable with that? Okay. Questions? Questions on that? Question? Okay.
Is the healthy associating to the dynamic variably?
No. It's the one in person. Yeah. That's one of the reasons. Great question, Mustafa. That's one of the reasons we refer to it. We're very specifically referring to it as the healthiness with respect to person, because there's also a healthy stock. Good call. This is why we have what are called namespaces in programming languages, and they basically mean that the name is not known by everyone, so they don't conflict with each other. They live in a certain context. So this is person's healthy is not really seen by and doesn't interfere with in the main class. Okay? Okay, ladies and gentlemen, you've seen me put that in. I would like you to tell me, on the basis of this, how would I now have a count of the number of ill people? Suppose I want to count them up and not be clever by subtracting 1,000 from, or the count healthy from 1,000. How would I count the number of ill people in the same sort of way? Okay, add statistic, and I'll do count ill. Come on, you folks should be able to fill this in for me. Those are computer science background. Okay, this is exhibiting truculence. So pardon me while I detrucularize this. Okay, that's the most interesting error. Those who are software developers, take note of that. Wow, that's really interesting. So pardon me. Okay, that's really interesting, man. So pardon me while I attempt to probe this to fix it. So fortunately, you folks can push forward while my situation is more grim. Okay, yeah, there's something really funky going on. Okay, wow. Okay, that's really interesting error. Okay, so please go add that other statistic. It'll be count ill, and it'll be just like this, except it'll be person dot ill, right? Yeah. Okay. So forgive me as I just try to figure out the etiology of this error. Okay, so things are fine here. It's not a key layout problem. It's looks like Eclipse has crashed. I've never seen this before. Okay, I'm gonna destroy it. Okay, there we go. Boom. Save early, save often. Build early, build often. Run early, run often. Mark my words. Okay, so I'm going to call this again. Okay, so ladies and gentlemen, you should be able to move forward even as I lag. So next, I'd like you to add to that chart that was showing in the main class. I would like you to add in value items, data items to that chart, which count the number of people in the population who are healthy and ill. And you would do so by calling population.countHealthy, population.countIll. I'll be following right behind you here, but the idea is simple. The idea is you go up here, and you're going to add these in, add data item, and we will plot population.countHealthy, and we're going to similarly add population.countIll. Now, you folks have probably already told it how to do that, but I'm behind because of my crash. Okay, so let me just go do it in front of you. Count ill, and this is going to be count ill. There we go. And And here we go. Population dot count ill. Okay, so what have I done? Let's step back in case anyone is not caught up. Let's rehearse what we've done. We've added a person class. We've added a oval to the person class. We added a state chart. We added a variable called color. That variable was of type color and was given the initial value black. With the state chart, we had two states and a transition between them. The transition between them was a rate transition with a rate of 1 over the mean time healthy within the main class. We have a healthy state, which when we enter it, we assign green to the color, and an ill state where we assign red to the color when we enter that. I then took this, and I wanted to find out how many people, we ran it and made sure it looked okay, and then I wanted to find out and plot in the main class how many people are healthy or ill. To do that, I did what, ladies and gentlemen? I defined two statistics associated with the population. These statistics defined a thing called count healthy, which is a method that it creates for me, which goes through each person in the population called item in turn, and it asks the state chart for that person, is this healthy state active? Similarly, it goes through, for count ill, it goes through each person in the population called item in turn. It asks for their state chart, is this certain state called person.ill active? If so, in both cases, it counts that person. On the basis of that, on this chart, I added two things to the chart. In addition to plotting these stocks here, I further am plotting population.count healthy, population.count ill. Does that make sense? Okay. Anyone have a question about where we're at? Because now is the point where we're going to start comparing. And we're going to go pretty quick in terms of using this model to make a few points. Are you using Linux? I am when I use Linux with it. It's an Eclipse bug, I think, and you and I need to go talk with Greg Oster and figure out why Eclipse is having this bad behavior. It's not any logic alone. I've had it happen in other Eclipse uses too, and it's some pathology with Eclipse. So be careful about using autocomplete. That's all I'll say for now. Other than that, it seems to work okay. It's just an autocomplete pathology. Okay, other questions? Ubuntu? Okay, yeah. I'm doing Kubuntu with XFCE. Yeah. Okay. So, ladies and gentlemen, what should we see when we run this model? Anyone? What do we see? I'm sorry? Similar trajectories. Okay. So we don't even see that there's 4 lines here. Why not? Sorry? Indeed. And that's the operative thing. So let's zoom into this, for example. You'll see that there actually are slight divergences here between what on the one hand is predicted via the system dynamics model and otherwise is predicted via the agent-based model. Why are there those divergences in place? Why do we see this kind of difference here?
One of them, I think, is discrete and the other one.
One is discrete and the other is continuous. Good. One is stochastic. There's uncertainty in exactly how many people. Each person is rolling a dice or flipping a coin, as it were, to figure out if they get ill this time. And on average, it adds up pretty well, pretty closely. But there are some divergences between them associated with the vagaries of chance, associated with the fact that with the stock and flow model, we actually have fractional people. 32.2 people are ill versus 32 or 33. Okay? So does this make sense to people? And sort of what you see here. Okay? So this is kind of the case where they are most comparable. Now, I would note that if we run this again, take note of the vagaries of this, you know, the sort of what it looks like in the center point here. If we run this again, will we see exactly the same thing? Well, let's go, if you go click on the experiment, and you scroll down here, you'll notice it's using a random seed. We can use a fixed seed, otherwise it uses a one that's chosen based on the current time. And so if you run it again, you will see slightly different patterns. So let's speed this up here. Okay, and I'm going to zoom into that same region. Very, very similar, but there are some, there will be some slight differences according to chance with some runs compared to others. Okay, so we see here odd correspondence of the two models, and the fact that they are yielding pretty darn similar results. In this case, the differences are quite visible at this level. Previously, they were sort of evening out. So a system dynamics model can be a very powerful summary of what's going on, but it does have its limits, ladies and gentlemen. So we're going to now explore some variants of what we've seen here to understand what some of those limits are with respect to sort of this simple first-order delay type formulation. Okay, ladies and gentlemen, I'd like to now go back and revisit this state chart, and I'd like to change this transition here to go from a rate to be a timeout. And what value to use for that timeout? Well, I'm actually going to go copy this. And here it's a timeout of main.mean time healthy. Okay? So now, within the agent-based model, we're going to have people who are healthy for the same average amount of time. What will the difference be now? So, are they healthy for the same average amount of time? They are. Well, will there be much of a difference in terms of behavior? What do you think we'll see now? Okay. Okay, so they're all going to change at the same time. Let's go watch this, okay? Where are the ill people? Hands. Look at that. Boom. Okay? That was Annus Horribilis. It was a very bad year. Year 20. So suddenly we had everyone change, right? We've just changed from a memory-less formulation to a memory-full formulation. From a situation where you have the same kick of the can no matter how long you've been in that state, you have that same chance of 1 over the mean time of getting it per year, for each successive year, no matter how long you've been there, to a situation where it exactly depends on how long you've been there. Now, it precisely depends on how long you've been there. It's not memory less, it's memory full. It's relying completely on how long you've been there. If you've been there less than 20 years, there's no chance you've transitioned. On 20 years, you're going to be going within that next year. So we see a difference here going from a memory less to a memory full transition. Ladies and gentlemen, riddle me this. Suppose now I want there to be the same mean time until people become ill, but I want it to be drawn from a different distribution. Tell me, the original formulation where we had rate, let's go back and switch it back to that just so we can see exactly what I'm talking about. When we had a rate here, we were actually drawing this value from a distribution. What distribution? From which distribution was the actual time for a particular person drawn? It was drawn from a what distribution? An exponential distribution? An exponential distribution? So we were drawing for each person, it was actually drawing a value, quite literally. When they came into the state, it drew a value for when to fire this transition from an exponential distribution. It picked one of these with a certain probability, with a certain probability density is given by this distribution. So sometimes for a given person, it picked way out here to the right at a long period of time. So this is residence time. It says, oh, this person will live a long life before they become ill. And some people it picked way down here, close to the x-axis. It's gonna be a short period of time. They're gonna be leaving in a short period of time. And for each person, when they came into that state, it would actually pick the time from an exponential distribution. When I say an exponential distribution, this is a curve. It's going to integrate to 1. Remember your probability. It integrates to 1. It's going to be described, it's going to be proportional to e to the minus lambda t, and the constant of proportionality is actually 1 over alpha. And so we're going to have a situation here where it is drawn from a distribution that's characterized exponentially, and some people are going to have a higher value and some people have a lower value. That's what's going on right now with the rate transition. Do people understand that point? Yeah. Okay. So we want now to do something different. We want to draw the value from a uniform distribution. Okay? How would I do that? I want each person to have variability. I don't want them to all go at once, but I want to draw it from a uniform, so it's uniformly distributed between, say, half of, between 0 and twice the mean time healthy. Uniformly distributed, some people go immediately, some people stay as long as twice that, but uniformly distributed. How would I do that?
1 over uniform 0 to main dot time.
Okay, okay, so it's something about uniform from 0 to twice mean time healthy. That's right. There's going to be an element of that. But what sort of transition will it be? What sort of transition would it be where we could tell it, leave after exactly this amount of time? It's a timeout. Timeouts aren't limited to fixed timeouts. You could have timeout of this, and what would the timeout be for a given person? It would be uniformly distributed between 0 and twice mean time healthy. Okay? Some people would leave immediately. Some people would leave it twice. This is a custom distribution. You can put in any number of distributions. You can put in a beta distribution. A normal wouldn't really make too much sense because it would suggest some people could have a negative time, but we could have a log normal, a gamma, different distributions. So the timeout here is itself drawn from a value. So when they come in, it picks a value from this. Now, ladies and gentlemen, is this memoryless? Is that if we draw their time of leaving the state from a distribution such as that, is there a chance of leaving in the next year independent of how long they've been there? No, it's not independent. How can we What would be one intuition for why it's not independent?
The time was like 39.
Yes. 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 If they're right at the end of this eligible time, they've got to leave in the next little bit of time. There's just no question about it. So that's there's going to be certainty at that end that they're going to leave, whereas there's not that certainty early on. So it's definitely not going to be memoryless. It's not going to be as crude as kind of a fixed timeout, but it's going to not be memoryless. So here we have a transition, and we see it diverges quite a bit actually from the stock and flow. Is the stock and flow memoryless? Yes. I mean, in terms of your chance of leaving that first stock, it's independent of how long you've been. As far as it's concerned, as long as you're in this first stock, it doesn't matter whether you entered that 2 weeks ago, 2 months ago, 2 years ago, 20 years ago, your chance of leaving given by what? Your chance of leaving per year is given by what? What expression? No matter how long you've been here, your chance of leaving in the next unit time is given by 1 over the mean time. This new formulation that was used for the agent-based model, it's quite different, right? I mean, it diverges quite a bit. We've told it to draw it from a distribution. It's not a memoryless distribution. It's memory full. And you can see it does diverge from what a stock and flow model would calculate there. Now, how might we try to approximate that with a stock and flow model? How would we try to approximate it? So suppose someone gave this to us. They said, you know, I've analyzed the times it takes people with diabetes to develop end-stage renal disease, and it's actually characterized by this distribution. Does that mean we can't put it into a stock and flow at all? I'll give you a hint. Stock and flow models are computationally universal. You could do it. How would you do it? Riddle me this. Think about it. What would be a way that we could capture this in a stock and flow model, capturing memory full behavior? I'll tell you a secret. I told it to you last time. How do you capture in a stock and flow model memory full behavior? Like the fact that takes a while for people to get to older age. How would you do that? You'd create you'd have a series of stocks. And the first stock would have a certain chance of leaving per unit time. The second stock would have a certain chance of leaving per unit time. The third stock would have a certain chance of leaving per unit time. And those would be different for each successive stock. So, and you'd transition between the stocks according to how long you've been in the system, and thereby your chance of leaving the system, going to that ill state, will be different for each stock. It can be done. It's just you're dividing into granular categories. Here you can actually specify quite nicely an arbitrary distribution and just say, okay, use this distribution for how long it takes to develop this, okay? And it will just go off and do it. So you can do it in a stock and flow model. You can approximate it, but you can do it a little bit more, facile fashion, more transparent fashion. One where you don't have to change the structure of your model to capture the vagaries of the data, like the distribution. You can capture it directly with a distribution. But a stock and flow model can do it. Don't think you can't. And there's lots of advantages for using a stock and flow model in general. Among other things, it can be much quicker than simulating this whole agent population. But stock and flow models, with a single stock, it's going to be memoryless. Multiple stocks are not memoryless. Your chance of leaving a set of 2 stocks is not independent of when you came in. Okay. in general, if you have a set of stocks. Okay, ladies and gentlemen. So let's go one step further with this model. We're going to now take this model, and we're going to expand both the system dynamics and the agent-based portion of it. Okay, ladies and gentlemen. For the system dynamics portion, we're going to actually, let's go back to the agent. Let's change them back to use this rate. Here we go. Rate. Boom. So now they're memoryless again in the same sort of way.
How can we save those different types of models like this? We should save them in simulation or what?
Oh, like if we want to experiment with the different ones? Very nice question. So unfortunately, this is under-conceptualized right now in AnyLogic. And what this means is different simulations, different experiments. You can have different assumptions about parameters, but you're using the same underlying model structure is assumed. So you'd really have to, in this version of AnyLogic, you'd have to do one of two mildly unpleasant things. Either you'd save a new version of the model to a new file name, or you would take main and you would create a copy of that. So you could have main 1, main 2. And you could run, some experiments could run main 1, some experiments could run main 2. That would also be an option. But it's not so nice because maybe you want main 2 to use person 2, and main 1 would have to use person 1. So it's not that clean. So saving away successive versions of the whole model is maybe a little bit cleaner. Yeah. Okay? So ladies and gentlemen, I would like to go here and I would like to add an immigration flow that's going to be given by 100 people per year. 100 people per year. How do I do that? Okay, I'm going to add in a flow, and it's going to be healthy people, healthy immigrants. Okay, so this is immigration, and I want to make it 100 people per year coming in. Okay, there we go. Rate of 100. Okay, ladies and gentlemen, I now want to add an immigration flow for the agent-based model. How do I do it? I haven't told you yet. So, sorry? Those who have seen these things before may recognize it. But what we're going to introduce is a new construct. I mentioned it last time very briefly, but it's called an event. And it's going to be called immigration event. Where did I pull it? From whence did I pull it? I pulled it from general, and I dragged over this from general, and I dragged over event. It's going to be called immigration event. This is going to be based on a certain rate, and the rate is going to be 100. What does that mean? A rate of 100. What does that mean? 100. It's going to fire on average 100 times per year. Or, to put it another way, the average time between firings is going to be 1/100th of a year. Right? Okay. So, when this fires, what is going to happen? Now there's the rub. Okay, so what's going to happen? Should we do it? Let's do it. Okay, ready? This is what we're going to do. This dot add population. Boom. We're going to add someone into the population. So this is adding them in. Now, if people had lots of parameters, you would specify the parameters here with the characteristics of the person, for example. But we're just going to add in a person to the population. So 100 times a year on average, we're going to add someone into the population. Okay? That's immigration in an agent-based model compared to immigration in a stock and flow model. I'm trying to sort of have you spot some of the similarities and spot some of the differences here. Immigration here, it's the value of a flow in the stock and flow model. Immigration in the agent-based model, we're actually 100 times per year, we're actually adding people in. Does that make sense? Okay, so can we run it? What do you think we're going to see? Remember, we changed people back to be memoryless. What are we going to see? What's going to happen over time? Well, the population is coming in thick and fast. Where are the different lines? What's happening over time? Ladies and gentlemen, what's happening over time? Why is the blue going up and then stabilizing? At what value does it stabilize? Oh, come on, you've told me that already. And the problem set. What value does it stabilize? And why? Come on. Sorry? Yeah, it's 2,000. Why 2,000? The immigration rate is 100 per year times what? The mean time in that stock, right? It's at that point that the inflow equals outflow. What's the inflow? 100. What value would the stock have to have that if you divided it by 20, it would equal 100? 2,000. You have to have 20 times 100. At that point, it's going to be an equilibrium, right? And so it is. You'll notice in both the stock and flow model and the agent-based model, it has equilibria, sure. Just you can't compute them from it analytically with quite the clarity that you can with a stock and flow model like this, where you can actually reason about the inflows and outflows. But you notice that the agent-based model adheres to, it's subject to the same basic rules of equilibria and so on. We can use the stock and flow model to summarize what's going on in the agent-based model really nicely, actually. The agent-based model can capture some additional texture beyond that. So if we run this thing up, we'll see the population continue to rise, and it's not going to be terribly instructive. But you will have that initial stock in a equilibrium state. And, I'm going to pause it again, and I'm going to zoom in on this. And you'll see there's some differences here. By the vagaries of chance, the two are slightly off. Due to round off, you have an integer number of agents, whereas you have a real number, a real number with decimal points for the number in the stock and flow model. And they're going to be slightly off, and there's going to be stochastics. But pretty darn similar. Okay, ladies and gentlemen, now let's go back to person, and in the denouement, let's go change this from a rate to be back to our timeout, which is going to be uniformly distributed. There. Are we going to see equilibrium? Will we see an equilibrium for the stock and flow model? Do you think? For that first stock? Or conceptually for the numbers that are healthy, will we see that? Will that occur in an equilibrium? Will there be an equilibrium? Yes or no? Roughly? Will it be a deterministic equilibrium that will stay forever once established? No. Okay. So what's going on here? Oh, it looks, it's up. Somehow the colors are a little bit off, eh? There we go. Okay, that's better. So yeah, it approaches a form of equilibrium. In fact, the equilibrium is it's actually the same equilibrium. Why the same equilibrium? Why the same equilibrium? Let's try something wild. Let's try this, folks. Let's try this. What was a case where we saw totally different results between the two models? When we assumed what sort of distribution, or where we assumed what saying about that transition? When do we see very different results? Okay, yeah, it was constant. We assumed a constant timeout, right? Remember that, folks? So let's make it, what was that constant timeout that we assumed? Okay, yeah. So we're going to just make it mean time healthy. What do you think? Do you think they'll go to the same equilibrium or different now? Do you think they'll go to the same or different with this immigration context? Look at this. Annus Horribilis is arriving. Okay. Are they going to the same or different equilibrium? For this count healthy. It's going to the same equilibrium. Why? Well, we did have the sudden transition that was very different for that initial population. But now we have mixed in to people, the healthy population. Some people have arrived recently, some people have arrived later. They're all leaving after exactly an amount of time, but they're pretty well mixed in terms of, how many there are that arrived recently or later. And the net result of it is that the stock and flow model is a pretty good approximation to the equilibrium dynamics of this agent-based model, even though the agent-based model differs early on quite dramatically in terms of its behavior. Even though it's not memoryless, these individuals are not exhibiting memoryless transitions out of the healthy state. We can get equilibrium approximations from the stock and flow model that are actually shockingly accurate for sort of the average of what's going on. Even though they abstract away from a lot of details of the agents. They treat them as kind of memoryless in terms of their chance of going. You can get very good equilibrium behavior. So in terms of certain rough understanding of sort of equilibria associated with a model and so on, a stock and flow model can be very insightful. Sometimes we use, ladies and gentlemen, a stock and flow model to plan roughly, for example, where to intervene on a system, and then we use an agent-based model to figure out how to intervene in very detailed terms. How will it depend on an agent's history, the detailed planning of an intervention. But the stock and flow model can be very insightful, coming quickly to the situation, capturing it in rough terms. And is it wrong in terms of assuming memoryless behavior? Well, it's an approximation. Like all these models are approximations. But sometimes the approximations can be pretty darn accurate particularly for sort of rough quantities like equilibrium behavior. Even if in certain other types of disequilibria, like early on, we have just very dramatic differences between them. So, ladies and gentlemen, agent-based modeling affords us this very rich vocabulary to characterize agent actions. And if we want to reason about agent choices, we want to reason about how their preferences and how they'll choose things under different types of policies we might put into place. If we want to capture networks, if we want to capture their locations in space, if we want to reason about their history and have maybe an intervention that treats them differently based on their previous encounters, then an agent-based model can be really formidable in its insights. But don't treat it as if an agent-based model, because it has all these factors which a system dynamics model will typically, brush a little bit under the rug. Don't treat it as if you can't get profound insights from that system dynamics model. Even a rough system dynamics sort of characterization of things like equilibrium behavior can be darned accurate, even though it glosses over a lot of details. So what I've tried to do this lecture, for the first time, I've never actually delivered this lecture before, is try to highlight some of the interplay that goes on so that you'll be clear in your mind on the relationship between, on the one hand, these sort of state transitions and the different sorts of state charts and the different sorts of transitions you can see, and with stocks and flows. There is a mapping between them, and stocks and flows can be incredibly insightful ways of summarizing the state of an agent-based model. How many people are coming into this state? How many are transitioning between states? Very effective. And a system dynamics model can be very effective at reasoning about at a rough level the behavior expected, but it glosses over certain things. Particularly this memoryless assumption is one of the things that's its inability to handle certain types of heterogeneity in a scalable fashion. But they can prove extremely useful and valuable. Whereas an agent-based model, by capturing these extra levels of detail, we can capture things with much greater precision. For example, in simulating certain types of policies. So I've tried to shed some light on that. It's imperfect, but I hope that it helps you understand some of the kind of mapping between the stocks and flows and what they capture and what these state charts within a given person captures, and highlights for you things like how to impose a custom distribution. Now I want to close by a remark on something that I was planning to show, but we ran out of time to do it well. And so I'm going to phrase it to you as a challenge. There's a video on it, and you can go and watch the video if you want to, and I'll send you the link. But suppose now we have an agent, and they differ not just with respect to their healthiness with respect in general, but maybe we want to capture things like their change in their employment status as well as their health. Or maybe we want to capture different aspects of their health, whether they have diabetes or not, whether they have heart disease or not. How would we do that with state charts? Well, one very nice way is we have what's called the separation of concerns. Who's heard the term separation of concerns before in computer science? Okay, thank goodness. At least one. That's great. So with the principle of separation of concerns, ladies and gentlemen, to simplify our thinking about a complex system, and particularly structuring that system, it's really handy to be able to cut down the amount we have to think about at any one time, to place certain features, certain aspects of the system in one place and certain aspects in others. So if we're dealing with a big software system, we have certain code dealing with the front end, the user interface at one place, the business logic in another, and the back end stuff like with the database or data storage in another. We put them in different places. Each thing in its place, and everything a place of its own. This is really useful because it means you don't have to think about the whole hairball. And you can replace these pieces fairly independently of the others. You don't have to debug them all together. Or test them all together. You can test each at a time. And it's just a lot less mental clutter. And so it is with state charts. You can separate out different state charts for different conditions. This is very different from a stock and flow model, where if we want to keep track of people's age and track of people's progression on disease, we have to mix them all together in sort of a lattice, where they kind of progress along, say, this direction, the x-axis for age, and then the y-axis for maybe disease progression or something along those lines. This kind of has to consider, in a stock and flow model, all combinations of categories and progressions between them, and it becomes very cumbersome. Whereas with a state chart, we could have one state chart, say, for age. It's not the only way to represent it, but it's one way. So this might be an aging state chart there, and then we'd have one for disease progression. Maybe it's 3 here. And instead of having to consider all combinations, we just parse them out separately. We compartmentalize. We have each in its own little state chart. Are people comfortable with that concept? Okay, very nice, very modular. You could take one of these out, replace it by a different one. It doesn't affect all the others. You try this in one of these bigger stock and flow models, it gets really awkward. You have to change across the entire model to substitute it. It's a big mess. They're all tangled together in a most unseemly fashion. But here's my question for you. So, ladies and gentlemen, if we separate up these state charts, how do we have them interact? How do we have one state chart depend on another? How do we have the progression of one thing depend on another? For example, how do we have their likelihood of developing diabetes depend on their age? How would we do that? How in this model, ladies and gentlemen, have we had a certain feature depend on the state that they're in? How do we do that? We introduced a variable. And I would pose to you that's one way to do this. So you could have, for example, as long as they're in the youngest age category, they have a certain chance per year of going from this state to this. When they go to this age category, the next age category down, they have another chance per year. You could do it with a variable. And it's quite a clean way to do it. You could have this other state chart depending on the values of that variable, and the value of the variable set in state chart A, and it's used in state chart B. Could you have B influence A as well in that same sort of way? Could you have my HIV status influence my Hep C progression, my Hep C progression influence my HIV status? Yeah, you could, actually. There's no problem with doing that. You could have a variable that's used to communicate the other way. Not a particular problem. So with variables, you can have these communicating state charts. And I'll wing you a link to a video where it walks through an example where this is built up. It takes about half an hour. And it's a very sort of scalable, principled approach. There are interactions. These state charts, ladies and gentlemen, are not solitudes, but you don't have to deal with all this combinatorial explosion of all possible combinations of states that you do in an aggregate depiction of this. So you can have interaction between the state charts, but in a more surgical, specific fashion as captured by variables. Okay? So, ladies and gentlemen, that's all for today. For the next time, I'm going to ask you to take a look at two pieces of the puzzle. We're going to have agents. What has been missing in these agents? These agents, we can have these state charts to capture rich behavior. We can have multiple state charts. What's been missing? Tell me a big feature that's missing between them. Communication. They're atomistic. They don't interact at all. They can each be very rich, but they're not interacting with each other. They're not influencing each other. And we know influencing each other is a big factor in complex systems. So we're going to be looking at how you can use messages and networks to have them interact with one another in a rich way. Later in the class, we'll see how we can use stocks and flows for them to influence each other in hybrid models. But for now, they're going to be interacting with each other through messages across several types of networks. I'm going to ask you to take a look at that at the lecture on networks in more detail, because we're going to be hitting conceptually several key types of networks, including a very interesting class of networks called the scale-free network, which exhibits really interesting statistical properties, really interesting dynamic properties, and structural characteristics. Okay? So that's all for next time. Be sure to watch these videos, and thanks very much. Can I go to the immigration event? Add population? Okay, maybe because your population is called something else? Is it called POP? Oh, yeah. Yeah, this is a method call. Yeah. Yeah.